Section 5.1, Systems of Linear Equations. In this first video, we will cover systems in 2 variables, and then I'll do a second video for 3 variables. So, on this slide, I am showing the solution to a system in 2 variables. So, when we use 2 variables in algebra, it's going to be x and y. The solution is going to be an ordered pair that makes all the equations true. So when we say a system of equations, it just means more than one. So the problems that we're going to do in this first video are just going to have 2 equations and they will have 2 variables in them. The solution will be an ordered pair, a value for x, a value for y. So just to kind of go further with that idea of what is a solution, we're going to start out with an example that gives an ordered pair. So this negative 3, 5 is given, and we're going to determine if it is a solution, which is basically like if we had solved and got this answer, we would check it. And the way you do that is just to plug it into each equation, and if it makes both equations true, then it is a solution. So x is going to be negative 3, y is going to be 5. So let's start with our first equation. So this is what we mean by system. 2 equations. We've got this one, this is our first one, this is our second one. Together they make a system. So we're not answering separately for each equation. It's just one yes or no for the entire system. Okay. So for the first equation, if we plug in negative 3 for x and 5 for y, and we work that out, we're going to get a negative 27 plus 35, which does equal 8. 8 equals 8 is true. So we're good so far, but we can't say yes until we've checked the second equation. So let's try it. 8 times negative 3 minus 9 times 5. And we're going to work that out. So it'll be negative 24 minus 45. Same sign, so we add and keep the sign. And it is also true. So if it's true for all the equations, then we answer yes, meaning this ordered pair, negative 3, 5, is a solution to the system. So let's think about some other things that might happen when we do a problem like this. If we plugged into the first equation and it was false, we wouldn't even need to try the second. We could just answer no. If we plugged into the first and it was true, and then we plugged into the second and it was false, then that would also end up no. The only way, so false on the first, doesn't matter what the second one would be, is a no. The only way we're going to get yes is if it's true and true, then it's a yes. Okay, so there'll be a few problems like that to practice in the homework. There are 3 methods that we're showing here for solving systems in 2 variables. We have graphing, substitution, and addition. Addition is also known as elimination. You may have learned it as that in a previous math class. So graphing is usually the method that is taught first. Here at South Plains, we teach it in a developmental math class. I'm not going to go through how to solve by graphing in this class, but we will kind of talk about what happens graphically. But the 2 methods that we're going to use to solve are substitution and addition. But to help us understand that there are 3 possibilities for answers when we solve these systems, we are going to think about what would happen if we graphed 2 linear equations on the same coordinate system. Okay, and some of the things that could happen are obvious, and maybe the third one is not quite so, but let's just think about that. Probably, okay, here's our xy axis. We'll change colors here. All right. Probably the first thing that you think about is if we graph two lines on there, we'll just put two lines, then you would probably end up just drawing them where they intersect. And they would only intersect in one point. So as we look in our table here, that's the first thing that could happen. The lines could intersect. If that happens, then you have only one solution, and it is the point where they intersect. Okay, you'd get a value for x, you'd get a value for y. It would be that point of intersection. Okay, now since we're not graphing, we're going to be doing substitution and addition. What will happen is, as I teach you the process, we will be able to solve and get values for x and y when case 1 happens. Okay, let's think about what else might happen if we graph two lines on the same coordinate system. So another thing that might happen is they could be parallel. Okay, and look in our table, that's the second row here, parallel lines. Now think about in the first graph here, the lines intersect, and the intersection point is the solution. Well, in the second graph, they do not intersect ever. Therefore, there is no solution. Okay, so when your lines are parallel, the system has no solution because they never intersect. Now, we're not going to actually be looking at the graph. So when we're using substitution or addition, the way that we would know our answer is no solution is because we will end up with a false statement. Something like 1 equals 2. You'll have two numbers that are not equal, and that's how we know it will be no solution. The variables will disappear as we go through the solving process. Okay, the third thing that could happen graphically. This one's the one that is a little bit harder to think about, but it's possible that we could graph one line and then we get ready to graph the second equation, and it would be directly on top of the first. So you would not even be able to tell there are two lines there. It would look just like one line. And we say that the lines coincide. Now, again, think about if the intersection point is the solution. Where do these lines intersect? Well, they intersect everywhere on the line, and the line has infinitely many points on it. So, when this case happens, there are infinite solutions. We could not list them all. We will learn how to write them in this notation that you see here in the table. It's called set builder notation, and I'll show you how to use it when we do some examples. Now again, since we're not going to be graphing, the way that we would know there are infinite solutions is when we start solving, the variable will disappear and we'll get a true statement. Okay, like 3 equals 3. That will indicate infinite. A false statement indicates no solution. True indicates infinite solutions. We actually did that concept earlier in the semester with equations at the very beginning, and then also with inequalities. Okay, so we're going to start with the substitution method. This is probably something that you have done at some point in the past, but I'm still going to go through all the steps and do several examples. The first step says, isolate one variable in one equation. So you can pick x or y, but notice then it says the best choice is a variable with a coefficient of 1 or -1. So instead of reading all this to you, let's focus on that first step in this first example. So instructions say solve by substitution, and we have two equations. Now normally when you look at a system of equations, they'll be given one written on top of the other. But for substitution, I went ahead and put them side by side to give us some room to work underneath. On your homework, you'll just see them written lined up one above the other. Okay, so step 1 said, isolate one variable in one equation. The best choice is the variable that has a coefficient of 1. So let's look at all our coefficients. On the first equation, we've got 3 and 2. On the second equation, we've got 2 and 1. So there it is. This y right here is the variable that I want to isolate because it has a positive 1 as its coefficient. I can isolate it in one step. So I'm going to leave the y on the left, subtract the 2x, we still have a positive 1. And now the y is isolated. If I had chosen any other variable, I would have had to do 2 steps and I would have to divide. Let's say I were solving for this x. I'd end up having to divide by 3, which is going to cause some fractions, and then it'll make it much more difficult than it needs to be. Okay, so we've completed step 1. Step 2 is substitute the expression found in step 1 into the other equation. So you're going to take this negative 2x plus 1, whatever your variable equals, and you're going to substitute it into your other equation. For y, because we're saying y is equal to negative 2x plus 1, then we can replace y with this expression. So we're going to equation 1. We're going to write the whole thing down. We write the 3x, the plus 2, but when we come to y, we're going to replace it with negative 2x plus 1. Bring down the equals 4. Okay, so now I need to solve that equation. That's the next step. The reason the substituting helped us is because now this equation has only x in it, has only one variable. And once you have just one variable, then you can solve for that variable. So let's solve. We'll start by distributing the 2. So it'll be a negative 4x plus 2. And then combine like terms. 3x minus 4x would be a negative 1x, or just negative x if you prefer. And then let's subtract 2 from both sides. And divide by negative 1. And that gives us negative 2 for x. Since we were able to get a value for x, then we know that this system does have a solution. We know the x, we need to know the y that goes with it. Remember, a solution is an ordered pair, has to have an x and a y. So to get the y, we're going to take this answer that we just found. We could plug it into one of our original equations, and that would work. Or I like to plug it into the equation where the y is already isolated. So if we do it that way, we'd have y equals negative 2, and then replace the x with the value we got, which was negative 2. And then we would do the operation. It would be 4 plus 1, and y would be 5. So now we have a value for x, we have a value for y. Let's go ahead and write the solution as an ordered pair. So parentheses, it'd be negative 2, comma, 5. This is how we want to write our answer. Now certainly we could check it. Maybe we should do that at least once here. It should make both of our original equations true. So let's go to the first equation and plug in negative 2 for x and 5 for y. We should get 4. Let's see, it'll be negative 6 plus 10, and that is 4. All right, so true for the first, and then let's check the second. I'm going to squeeze it in down here. So I'm looking at my original equation, and I'm plugging in -2 for x and 5 for y. So -4 plus 5, and that is 1. So 1 equals 1, true. So just remember, you can always check your answers when you solve a system of equations. Okay, let's go ahead and try another example. Sometimes the first step may already be done, which it is in number 2 here. We already have an x isolated in our very first equation. So check for that. If there is a variable that is already isolated, meaning it's on one side of the equal sign all by itself, then you don't need to do step 1. Just go ahead and use that equation. And go on to step 2, which is to substitute. So your variable that's isolated is equal to this, then that means I could replace x in my other equation with 4y minus 8, because that's what x is equal to. So now we go to the second equation. We still need the 5. Replace the x with 4y minus 8. Bring down the rest of the equation. And now this equation has only y in it. It should always, once you substitute, the resulting equation should have only one variable in it. Sometimes it will be x, sometimes it will be y, but just one variable. Okay, so let's go ahead and solve. We're going to distribute the 5. And then we are going to combine like terms. So we've got 20y minus 20y, that's 0. So we actually do not have a y at all. I'm just going to drop down the -40, and we also have -40 on the right side. So we end up with a true statement with no variables in it. And if you go back to that slide that had the 3 possibilities, we know that a true statement means this system has infinite solutions. Now, by saying that, it does not mean that we could pick any random ordered pair and it would be a solution. They are only the ordered pairs that are on the line. Remember graphically what this means. It means if I graphed the first equation and then I graphed the second would be right on top of the first. So every point on the line is a solution. But if I just pick some random ordered pair out here maybe, or over here, those would not be solutions. So how are we going to, describe the solution set? It's called set builder notation. Let me go ahead and write that down. You don't have to memorize that name or anything. I just want you to be somewhat familiar with it, so when I use that term, you'll know what I'm talking about. It always starts with a brace, and for these systems, right after the brace, you're going to put in parentheses x, comma, y. Now, what we've written so far means the set of all ordered pairs. Okay. Then you're going to put a bar, just a straight up and down bar. In math, that bar means such that. Okay, so we've got this set of all ordered pairs such that, and then we want to indicate that the ordered pairs are on this line. Well, we can do that by just picking one of the original equations. It does not matter which, because they are both the same line. So I'm just going to go with this first one here, and I'm going to write it on the right side of the bar. Because every point, every ordered pair whose x value is 4 times y minus 8 is going to be on this line. So this is just a way of saying the set of all ordered pairs such that they are on this line. And that is the solution for this problem number 2. Okay, let's go ahead and try one more example by substitution. Here again, we have equations that have the variable already isolated. In fact, both have the y isolated. So we can go straight to substituting, and it actually doesn't matter whether we take this expression here and plug it in for the y in the second equation, or we could have done it the other way and plugged in the 3/4 x plus 7 into the first equation. Either way is fine. Okay, so I'm going to go ahead and replace this y with negative 1/2 x plus 2. So we replace the y, then we bring down the right side of the equation. And now it only has an x in it, so we need to solve it for x. To solve for x, let's start by clearing out the fractions. Our LCD here is 4, so I'm going to multiply every term by 4. Okay, when we do that, we're going to divide 2 into 4, goes 2 times. So I've got a negative 1 times 2x would make that a negative 2x. And then 2 times 4 will make this 8. Over here, we're going to divide the 4's out. So we'll just get 3x. And 7 times 4 is 28. Okay, now we need our x's on the same side. It does not matter, left or right. I'm going to go ahead and subtract 3x. And then I'll move the 8, minus 8 on both sides. That's going to give me a negative 5x equals, and I'm going to do 28 minus 8 would be 20. So we divide by negative 5 and get x is negative 4. So we know that there is going to be one solution this time because we were able to find a value for x. Then we're going to plug that into our first equation. Since it already has y isolated, well, they both do, but we'll just go over here since we've got some room. So we've got negative 1/2, and then we're going to plug in negative 4 for x. So we've got negative times negative is going to make it positive. Half of 4 is 2. Or if you needed to, you could, work out 1/2 times 4 over 1 equals 4 over 2 equals 2, if you needed to do it that way. And then we drop down our plus 2. So y equals 4. And then remember, we're going to write the final answer as an ordered pair whenever we find x and y, parentheses, put the x value first and then the y value. And that is our solution. If we had graphed these two equations that were given, they would intersect at the point negative 4, 4. And of course we could check the answer. I'm not going to show the check this time for sake of time, but remember that you could check it, and sometimes they're easy enough to check, in your head. This one would be pretty easy to check. Okay. Let's move on to the addition method. Both of these, substitution and addition, are algebraic methods for solving a system. Really, to me, there's not one that's harder than the others, and it kind of depends on how the equations are given as to which one might be better to use. There are many times where either one would work fine. We'll talk about that a little bit more after we learn the addition method, as far as, if I were given a choice, which one I might choose for a particular problem. So first step here, write both equations in the form ax plus by equals c. So with that first step in mind, let's go ahead and look at our first example. And here the equations are given, one written above the other. We do not have the x and y on the same side. Step 1 was saying we need x and y on the same side, the constant on the other side. So let's go ahead and rewrite these. We are going to, I'll just put it down here below. That first equation, I'm going to leave the 2x on the left. I'm going to subtract the 3y so that it'll move to the left. And then I'm going to keep the 9 on the right. And then on the second equation, I'm going to add the 3x to move it over. I'll still have the 4y on that side and the 8 on the right side. And I want the terms in order with the x's lined up, the y's lined up, the constants lined up. So that's step 1. A lot of times the equations will already be given in that form. Step 2 says, if necessary, multiply one or both equations by a number so that either the x coefficients or the y coefficients are opposites. By opposites, we mean opposite signs. So if you had a 3 and a -3, those would be considered opposites. So we look at the coefficients of x. We've got 2 and 3. And then y, we've got -3 and 4. So we do not have opposites right now, which means we're going to have to multiply by a number to cause that to happen. It doesn't matter whether we choose x or y. I might choose y in this problem just because they already have opposite signs, but it really doesn't matter. It would work either way. Okay, but you have to pick. You have to make that choice. So I'm going to go ahead and write down here, I am choosing to eliminate, which is why it's sometimes called elimination, y. I'm going to choose to make the y's have opposite coefficients, which is going to cause the y's to be eliminated. Now, once you've chosen that variable, what you need to think about is what is the least common multiple? Least common multiple for 3 and 4. In other words, like if they were the denominators of fractions and I needed to add them, I need the least common denominator for 3 and 4, it would be 12. So the LCM of the y coefficients is 12. So I have to multiply by a number that's going to cause those to turn into 12. Now I'm going to put that number on the outside of the whole equation. So I'm going to think about to turn 3 into 12, it needs to multiply by 4. So I'm going to write the 4 out front. And to turn 4 into 12, I need to multiply it by 3. I need them to be positive 12 and negative 12, but I don't have to worry about sticking signs on there in this case because since I've already got opposites, 4 times negative 3 is going to make that negative 12, and 3 times positive 4 is going to make that a positive 12. So the signs will be taken care of. So the next thing we need to do is multiply by the entire equation. That number has to multiply to everything, not just the y term. So let's write down what's going to happen when we do that. Trying to think if I want to go to the side or down below. We'll go down below. Okay, so if we multiply the 4 times the 2x, we get 8x. And 4 times negative 3y will be negative 12y. And 4 times 9. And then we distribute the 3. We get 9x plus 12y equals 24. And now look at your y terms. We've got negative 12 and positive 12, which is what we wanted. We wanted them to be opposites. Once you've accomplished that, then you add the equations together, which is why some books call this the addition method. So if we add, we're going to get 17x, 0y, so you don't have to write anything here. Now, if I didn't have the 17x, I would need to write the 0. However, 17x plus 0 is still 17x. And then we add on the right side, we are going to get 60. So we have an equation that has one variable in it. Now we can solve for that variable. So divide by 17, which does not divide evenly into 60. And this fraction cannot simplify. So it is going to stay 60/17, which is part of the reason I chose this example, because it has such a crazy answer. Most of the time, if you got 60/17, you might think, oh, I must have done something wrong, but not necessarily. Okay, sometimes it will have crazy fractions like that. So now we need to find the y value. We will plug back into one of the original equations. We don't have an equation like we did with substitution to go back into. So it's always back into one of the originals. Does not matter which. I am going to go into the first one. So I've got my 2 out front. I'm going to replace x with 60/17, and then that's equal to 9 plus 3y. So if I'm going to multiply by 2, let's think of this as 2 over 1. So that'd be 120/17. Now, we could then subtract the 9, and you'd have to get a common denominator and do some fraction work there. Or if you prefer, you could clear the fraction out. Let me go and show that. If we multiply every term by 17, then that's going to get rid of the fraction. So we divide the 17s, we'd have 120. And then we do 9 times 17 is 153. And 3y times 17 is 51y. Okay, now we're ready to solve. Let's subtract the 153. Is a negative 33. And divide by 51. So this fraction actually will simplify. We can divide the top and bottom by 3, which will make it negative 11/17. So we do have a solution to this equation. Let's write it as an ordered pair. It's 60/17, comma, negative 11/17. That is our solution. And this is a good example of why we need algebraic methods to solve these. If we tried to solve that by graphing, we could see that the lines intersect, but we would never be able to determine by looking at the graph that it was intersecting at this particular ordered pair. And you could check your answer. It would require, some fraction work, so this one would be a little harder to check, but you can certainly use your calculators to check as well. So this is the addition method. Let's go ahead and do another example. Look at your equations. They are already in the correct form where we've got x and y on one side. We've got constants on the other side. So then we need to choose, am I going to eliminate x or y? So I'm going to choose x this time. I'm going to eliminate x. So then I need to think about what is the least common multiple for these coefficients of x. 5 and 10. 5 and 10. Least common multiple would be 10. So since this one is already a 10, or negative 10, then I don't need to multiply it by anything. I just need to multiply the top equation. I want to make 5 become 10, so I'm going to multiply it by 2. So we do that to all the terms, and it would become 10x minus 4y equals 8. The bottom equation we're not going to multiply, it's going to stay the same. And that's accomplished what we needed, because now look at your x coefficients, 10 and negative 10. They are opposites, which is what we want them to be. Okay, that's your goal, is to make x coefficients or y be opposites of each other. One common mistake I see a lot is sometimes students forget to multiply the constant by this number. So make sure you do it to everything, even the number that's on the right side. Okay, next step, add the equations together. 10x minus 10x is 0. Negative 4y plus 4y is also 0. So it just turned out that it caused both variables to be eliminated. Then you do need to go ahead and write 0 on the left side. Don't just leave it blank. And if we add the right side, 8 plus 7. So now it says 0 equals 15, which is false. That's why you need to go ahead and write that 0 there. Then you can see, okay, this is a false statement, and that means no solution. And when you get no solution, you just stop right there and box that in, and you're done. Okay, next we want to go ahead and try a couple of applications. Systems of equations are a good way to solve many word problems. And I know that a lot of students are scared of word problems, but these are not really difficult. You're just going to read the problem. You're going to determine what your variables represent. That'll be your first thing to do. And then you'll have to come up with 2 equations from the problem. So let's read number 1. A new restaurant is to contain 2-seat tables and 4-seat tables. Fire codes limit the restaurant's maximum occupancy to 56 customers. If the owners have hired enough servers to handle 17 tables of customers, how many of each kind of table should they purchase? Oftentimes it's that very last sentence, how many of each kind of table, that tells you what you're looking for, okay? So use variables to represent that. I like to use X and Y, but really you can use whatever letters you prefer. So we've got 2 different kinds of tables. We've got 2-seat tables. So I'm going to put X is number of 2-seat tables. And Y then would be the number of 4-seat tables. All right, so we've got 2 variables. Then we need 2 equations. You always need the same number of equations as you have variables. So there are 2 totals given. They tell us 56 customers and 17 tables. So let's start with tables. X and Y are representing number of tables. So if there's 17 total, then we could say X plus Y equals 17. And then let's do an equation for customers. So let's think about the 2-seat tables. Each of those tables will hold 2 customers. So we would multiply 2 times X to get the total number of customers at the 2-seat tables. Plus, each Y could hold 4 customers. So we would do 4 times Y. And that would give us our maximum number of customers, 56. So these are the 2 equations for the problem. Okay, so now we're ready to solve the system. Here you could choose addition or substitution. Either one would be fine. As long as I have a variable that has a coefficient of 1 or -1, then substitution is a good method. And I do. In this first equation, I have 1 in front of x, 1 in front of y. If these coefficients were not 1s, I didn't have a 1 at all, then I certainly would not choose substitution. Okay. Addition, well, they are already set up in the right form for addition, so that would work fine as well. To me, on this problem, there's not one that's easier than the other. I'm going to go ahead and do addition again, just for another example of that method. So, we're going to look at our coefficients of x and y, and pick one of those to eliminate. So, I'm going to go ahead and eliminate x. So, these are the choices we're making. We're choosing to solve by addition, and we're choosing to eliminate x. And our least common multiple for x, we've got a 1 and a 2, would be 2. If you've got a 1, then it's always whatever the other number is. So, I'm going to leave this one as 2, then that means this one needs to be -2. So let's multiply that top equation by -2. So that'll make -2x, -2y, and also by the constant is a -34. Then the bottom equation is going to stay the same. And look at your x's now. They have opposite coefficients. So when we add, that's 0. -2y plus 4y is going to be 2y. And 56 minus 34 is 22. So then we divide both sides by 2 and we get y equals 11. All right, then we're ready for x. Let's go to the first equation. Just go back to one of your originals. Plug in 11 for y, so it'd be x plus 11 is 17. Subtract 11, and we get x is 6. Now, when we're solving a word problem, you do not have to write it as an ordered pair. We just wanted to answer how many of each kind of table should they purchase. If you've already stated that x is 2-seat tables, I'll let you just box in that x is 6 and then y is 11. If you didn't write this down, which I do want you to though, then you would need to specify it's 6 2-seat tables and 11 4-seat tables. And certainly we could kind of check to make sure that's going to work. We should have 17 total tables. Well, 6 plus 11 would be 17. And then for customers, if we did 6 tables that each hold 2, plus 11 tables that each hold 4, well, that would be 12 plus 44 would be 56, which is how many customers that we could have. Okay, so there's one example. Let's do one more word problem, and that'll be the last problem on this video. The perimeter of a rectangle is 44 inches. If the length is 2 inches less than twice the width, find the length and width of the rectangle. So you might choose to use L and W here. Go ahead and do that. Remember, first step, write down your variables, what they represent, which should be whatever the question is asking for. Find the length and the width. Sometimes in a problem like this, it might say find the dimensions of the rectangle, which would also indicate length and width. So this involves the concept of perimeter. Perimeter is the distance around a figure. For a rectangle, if you add up all the sides, the 4 sides, you get the perimeter. But let's think about that. We'll call these the length and these the width. If we add those up, we've got L plus L would be 2L, and W plus W would be 2W. So this is actually the formula for perimeter of a rectangle. Now, for our equation, for our system, it says the perimeter is 44. So we can take this equation, 2L plus 2W, actually I'm going to scoot that over a little bit. 2L plus 2W is going to equal 44. So just, if it says the perimeter of a rectangle, then that's what you're going to use, 2L plus 2W. And then the second sentence here, the length is, so we're going to do L for length, is means equals, so you put an equal sign, 2 less than twice the width. So we're taking 2 from twice the width. So we would put 2W, that's twice the width, and then take 2 away from that. It has to be in that order, okay? So anytime it says 2 less than, then the 2 would have to come after the minus. So those are the two equations. Then we are ready to solve the system, either by substitution or addition. This time we already have a variable isolated. When that happens, I usually choose substitution. But you don't have to. You could certainly move the 2W over and then solve by addition if you prefer. But I'm going to go ahead and show substitution. So I've got my L isolated, and I'm going to take this expression and plug it in for L in my first equation. So it's going to be 2 times 2W minus 2. Then don't forget to bring down the rest. Bring down the plus 2W equals 44. And now we're ready to solve. We're going to distribute the 2, 4W minus 4. And then combine like terms. And add 4 to both sides. So 6W equals 48. Divide by 6, and we get W equals 8. So we know W is the width. You don't have to restate that. We do need some units here. This problem is in inches, so that's going to be 8 inches. Now to get L, we're going to take that 8 and let's plug it into this equation that says L equals, so 2 times 8 minus 2, 16 minus 2, so L is 14. And again, you need inches on that. Okay, so let's check. We don't have to write it out, but let's just think about it. And maybe you do want to write it out. It should give a perimeter of 44. So if L is 14, and this is 14, this is 8 and 8. Well, if we add all that up, 14 and 14 would be 28. 8 and 8 would be 16. And that would end up giving us 44 as our perimeter. Also, we could check to make sure the length is 2 less than twice the width. Well, 2 times 8 would be 16. 2 less than that is the 14. So just kind of make sure that those numbers match with what the problem stated. Okay, so you may want to go ahead and do the first part of the homework. To practice this, it is good to get an understanding here before we move on to systems that contain 3 variables.